what is a velocity? So anybody would like to help us out here? Yeah.
Speed with a direction.
Speed with a direction. Okay, so let's start with that. That's a very physics-like answer. Thank you. So then my question is, what's speed then? If it's speed with a direction, what's speed?
Distance over a certain time.
All right, so it is a change in distance over change in time, right? Okay, and a velocity can be thought of that way as well. Change in distance over a change in time. It just, happens to have a directional component to it as well. So if I have some equation that is an equation of distance, so let's say this is distance as a function of time. Okay, so instead of it being y and x, it's s and t. So s is like the distance, t is measuring the time. Okay, so if I did the derivative of s, so that would be the instantaneous rate of change of distance per unit time. So, because if that's how I'm going to define my function, is this distance as a function of time, then s prime of t, the derivative of it, should be the instantaneous rate of that change of that distance per unit time. Well, think about that. Is that not the same thing as what we just said right here? Instantaneous rate of change of distance. Change in distance per unit time. What does per imply? Divide, right? Per, when you think about units, so much like feet, like miles per hour, right? It's miles over hours, right? So it's the same kind of thing. So it's the distance over time, but it's instantaneous velocity rather than, like a change over a certain interval, that sort of thing. So what we're going to find here is that velocity, so a function we could have for velocity, v of t, is actually equivalent to doing the derivative of distance. And think about the units. Distance would just be, like feet or whatever, and then the velocity would be something like feet per second. So it's the change in the distance per time, seconds, whatever it is. Okay? So units for that, let's say like we're talking feet, so the velocity would be maybe feet per second. It kind of it depends on what you're measuring in, but we'll say feet in seconds for the sake of this one. And if we go one step further than that, if I do acceleration, well, what is acceleration? What is that measuring? Or maybe let's start with this. Anybody know the units? If I'm talking feet in seconds, what would be the units for acceleration? Be feet per second squared. Okay. So what is acceleration actually measuring then? It's not velocity squared. It's the change in the velocity. Okay? So there's kind of a little hierarchy to this, right? Velocity is the change in distance. Acceleration is the change in velocity. So I could define acceleration as the derivative of what? Velocity, right? Okay, so these relationships are going to be key. Velocity is the change in the distance per time. Acceleration is the change in velocity per time. That sort of thing. So if I give you a graph of, it could be listed as a distance, or it could be listed as a, like, displacement is usually the word that's used. Then we can take that equation and we can come up with what the velocity would be at a specific spot. So, for example, and they talk a lot about particle motion, so I'm going to stick with that here. So let's say a particle's position on a number line is given by let's say t squared minus 3t plus 1, where s is in inches and t is in seconds. So what is the velocity of the particle after 2 seconds? Well, we know the velocity is the instantaneous rate of change of the position. So if we take that equation that we have there, do its derivative, that should be the velocity then. So we can apply that power rule you guys learned about the other day. So the velocity of this particle should be given by 2t minus 3. And if I want to know what the velocity is after 2 seconds, what do you suppose I'm going to do with that? Just plug in a 2, right? Oops. Should be a 2. Okay, so velocity is 1. 1 what? What should be the units? What is it? Except this one's in inches, so inches per second. So, yeah, the instantaneous velocity of this little particle is, after 2 seconds, it's going 1 inch per second. Okay, so here's another question for you. See if we can kind of expand on this a little bit. So, when is the particle turning around? When does it change directions? So think about this. We've got this little particle on this number line. Okay, so just visualize your number line. And it can only go one of 2 directions. And you can either go to the right or it can go to the left. Okay, and it's going back and forth. So, you physics people, maybe you can help us with this a little bit, those of you guys that have had histories of that. So when the particle turns around, what should be its velocity? 0. Because remember, velocity is a speed with a direction. So if my particle is moving this way, its velocity is positive. If the particle turns around, comes back the other way, its velocity is negative. So when it turns around, it goes from positive to negative, or it could go from negative and then turn around and come back positive. So at those places where it could turn, what has to be true about its velocity? It has to be 0, right? That's an important thing that we're going to continue to work on with particle motion is this is going to be when v of t equals 0. That's when the particle will turn around or change direction. So we have an equation for v of t, right? We just came up with 2t minus 3. So 2t minus 3 equals 0. And then we just got to solve that for t. Find the time, right? Because the question is when, right? So time should be our answer. So it should get 3 over 2, and that's after that many seconds. So apparently this particle heads off in one direction, and then after 1.5 seconds, a second and a half, it turns around, comes back the other way. And this is the only place where it's going to turn around, right? Because if there were other places where it was going to turn back around and come back again, I would have other solutions to this equation. And this is the only solution to this equation. So I know for sure this is it. That's the only one. Okay? So, all right. I'm going to do one more question with this little particle thing here. So what's the particle's acceleration? Notice I didn't give you a specific time because it's always the same. Yeah?
2 inches per second squared.
You got it. Always 2. Because if the velocity is 2t minus 3, the acceleration, remember, is the derivative of velocity. So it should be 2. And the units, yep, would be inches per second squared. Now, depending on the equation that you start with, your acceleration might be different depending on how much time has elapsed. But with this one, because of the way the derivatives worked out, we've got a constant for that a of t, so that acceleration always stays the same. Even though the particle's velocity is changing, okay, how quickly it's moving is changing, the change in that velocity is always constant. It's always 2. Okay. Okay, so let's see if we can apply this same idea to another kind of situation. We're going to look at a rock that's been thrown up in the air and see if we can answer some questions about the rock's position, velocity, acceleration, that sort of thing. Now, some of you guys that have had physics before, you've got some equations that you've probably got memorized at this point or have used quite a bit that you could apply to the same thing. Okay, I think the calculus makes it a little bit easier if you can do derivatives, but those old equations still do work too, so I'm not going to stop you from using them. So, okay. So let's say a rock is thrown in the air so that its height at any given time, let's see what they have the time in, t is in seconds. Oh, we'll do the height is in feet. So the height of the rock in feet at any given time in seconds is given by we'll do h of t equals 160t minus 16t squared. Now, even though I used h of t for this one, that's still a position type equation, right? Normally position equations, they use the s, and I'm not entirely certain why it's an S. You can talk to Mordike maybe about that and see if he knows. But position equations typically, if there's nothing else you can use, they use S. Now in this case, we're talking specifically about the height of an object, so they're going to use H. However, that is still measuring a distance of something, right? The height of the rock is how far off the ground it is, so it's okay to treat that the same way. Okay, so here's what I want to know. First question. How high does the rock go? Now, if you were in physics and you didn't know calculus, you would probably start thinking about this parabola and what it looks like, right? Try to figure out where the vertex is, because that's going to be where the top of the rock's journey is going to be and all of that. However, what do we know about the velocity of the rock when it's up at its highest point? The rock goes up, it's at its highest point, and then it comes back down. What's the velocity when it's at its highest point? 0 again, right? So let's use that to our advantage and to figure out where this thing is at. So the velocity equation, we're going to need that. So we're going to have to do the derivative of the h to get this. So that's 160 minus 32t. And we said the rock is at its highest point when the velocity is equal to 0. So 0 equals 160 minus 32t. So we solve that for t. It's going to be essentially just 160 divided by 32, whatever that is. So 5. Now, have I technically answered the question yet, though? What question have I really answered right now? How long it takes to get to its highest point. I want to know what is the highest point. What is the height? So what do you suppose I should do with this 5 here then? Right, go back to the height equation, plug that thing back in for t, and see what you got. Because remember, this original equation tells you the height of the rock if you give it a time, right? We know the time, we want the height, so we can just plug it in. So h of 5, 160 times 5, minus 16 times 5 squared. Yeah, please use your calculators on that one. Let's see what we get. So, should be 400 right on the nose. So apparently this rock is going 400 feet in the air. I'm guessing a human being did not throw that rock. All right, good. So that's how we can answer a question like that. So let's see if we can answer something like this. What is the velocity of the rock when it's 256 feet above the ground? And because it's actually going to hit that mark twice, let's answer it for both. So what is the velocity of the rock when it's 256 feet above the ground, both going up and going down? So we need to figure out the velocity. And we have an equation for velocity. This 160 minus 32t. But that velocity is a function of what? Time. And was I given a time to work with here? What was I given? A distance, a height, right? So I need to take this height and convert it into a time. So I'm going to have to go back to my original equation, right? The height equation to do that. So I want to know what's the time when the height is 256. So I'm going to come back to this velocity one, but I need to solve this first. 256 equals 160t minus 16t squared. I want to know what is t when the height is 256. So I got to go with this. Now this is a quadratic, and I can add these terms, or add this term, subtract that term. Do some shuffling around here, so I've got 16t squared minus 160t plus 256 equals 0. And I believe all of those are divisible by 16, so I could just divide 16 out of everything and simplify this down quite a bit. Let's see, 256, yeah. So we got that then. All right, so can we factor that at all? Two numbers that multiply to 16 but add to negative 10? We can, right? What two numbers work? Yeah. So we got two answers, t equals 2 and t equals 8. Huh. Does that make sense why there's two answers? Because the rock goes up and the rock goes down, right? We said we want to do both. Well, there you go. There's your two times that you need. Which one do you suppose is on the way up and which one's on the way down? 2's on the way up, 8's on the way down. Now let's double check this. What should be the velocity of the rock on its way up? Should it be positive or negative? Should be positive going up, and as it comes back down, it should be negative. Okay, so when we plug these numbers into our velocity, we're expecting to see that. So we'll see if that's the case. So v of 2, 160 minus 32 times 2. So that velocity, what do we got? Yes. So on the way up, 96 feet per second. On the way down, 160 minus 32 times 8. Negative 96 feet per second. Huh. People from physics, does that make sense? That at the same height, the velocities would be exactly opposite on the way up as on the way down? Because everything is symmetric. Everything's balanced that way. So, yeah, that makes a bit of sense. And the velocities worked out positive and negative the way we expected to. 2 seconds, it's on its way up. It's a positive velocity. After 8 seconds, it's on its way down. That's a negative velocity. Yeah, that works. Let's go back up here. We'll ask another question about our rock. So what is the acceleration of the rock at any time t? But you guys can tell me this one very quickly. What is the acceleration? Negative 32 what? I'm not doing meters though. Feet. Huh. Again, physics people, red flag, right? Negative 32 feet per second. That should sound familiar, right? What is the acceleration due to gravity all the time on every object on the planet? Or in feet per second, negative 32 feet per second squared all the time, everywhere on the planet. Well, plus or minus depending on if you're in the mountains or whatever. But, at sea level. So this should make some sense that way. So gravity is an acceleration, right? We've all heard this before. Gravity is always working on you, and it's acceleration. It's a force, but it's also an acceleration. So no matter what happens, velocity of things can change as we toss objects around and all that, but this acceleration is always there, this negative 32 feet per second. If we were working in meters per second, it's 9.8, but same idea, okay? So that makes a bit of sense that acceleration would be constant in a situation when you're tossing a rock up in the air, okay? So, when does the rock hit the ground? So there's a common misconception with a question like this. There are some people that say, oh, when the rock hits the ground, the velocity should be 0 because the rock's sitting on the ground, right? But that instant the rock hits the ground, is the velocity of that rock 0? No. It hits it with some force, right? It has some velocity behind it when it hits. So I can't go that route with it. What am I left with here? Yeah. All right, so that's we can do that little trick, sure. What I was trying to get at is, though, it's essentially when the height is 0, though, right? Is one of two places when the height is, or one of two times when the height is 0. But also, yes, because of the symmetry of this thing, it's however long it takes to get to its highest point, it's going to take twice as much time for it to come back down and hit the ground. Okay? So if we do it that way, how long does it take to get to its highest point? 5 seconds. So we should be looking at 10 seconds for it to hit the ground. Okay? Let's verify that real quick with the height equation, though. So the height set equal to 0. So if we solve that equation, so let's see. So we can do a little bit of factoring here. We can take out a 16t, and that will leave us with 10 minus t. So there are two solutions to this equation. What are the two solutions? 0 and 10. So let's think about that. So at t equals 0, at time equals 0, the height is 0. Does that make sense? That's where it started, right? Before it got tossed. And then after 10 seconds, just like we thought it was going to be, right? That double that time it takes to get to its highest point. Then it's going to come back and hit the ground. So this was the start, and this was the end of this rock flying in the air. So, good. I think for today I'm gonna call it good. I want you guys to do some reading, though. There are going to be some other example problems in your textbook that are very good. I haven't through an entire one with you guys yet today, but I think you got enough of a head start here where you should be able to get through the rest of this okay. So, all right, we'll stop there.